Here we have an interesting and an important question. We have a block hanging from a spring and inside water. The spring constant and other data of the system is given. This block is initially at a height of 40 centimeters from the surface of the vessel. The density of the metal is given. Now what happens is that the spring is cut and we need to find out the rise in temperature of water. So the first assumption or consideration you have to make here is that all of the energy that is lost in this system is converted into heat, which is used to rise the temperature of the system. Now for that, let us find out the initial energy of the system, which is lost from the initial state to the final state. So for that, initially the system had potential energy stored in the spring, potential energy stored in the block. Let us see what happens. Potential energy of the spring initially was equal to half k x square, where k is the spring constant and x is the extension in the spring. So you have to first find out the extension in the spring initially. For that, we write Newton's law equation on this block in the vertical direction. Therefore, for this block, 1.2 g acts in the downward direction. There is a buoyant force in the upward direction and a spring force equal to kx in the upward direction. Now buoyant force, let us find out the buoyant force first. Buoyant force is always equal to density of the liquid into the volume submerged into g, that is rho liquid v submerged z into g. Therefore this can be written as 1000 density of water into volume submerged. Volume submerged is the volume of the mass, that is equal to mass upon density, that is 6000 into g. This comes out to be equal to 0.2 into g. Therefore the buoyant force we know as 0.2 into g. Therefore what we can write now is that kx plus 0.2 g is equal to 1.2 g. Therefore kx is equal to g. Now from this we get x is equal to g upon k, that is g upon 200. By filling in this value over here, we get potential energy of the spring was equal to half into kx into x, this is equal to half into kx is equal to g, and x is equal to g upon 200, that is equal to g square upon 400. This was the initial potential energy of the spring. So taking the value of g as 10 meters per second square, we get this as 0.25 joules. Therefore this much potential energy was stored in the spring, which got lost when the spring was cut, due to which the spring returned to its natural length. Also this block was initially at a height of 40 centimeters, but later on it fell down by 40 centimeters. Therefore there is another loss of gravitational potential energy. Let us calculate the initial potential energy of the block. Potential energy of block initially is equal to mass 1.2 into g into height, that is 40 upon 100, that is equal to 2.4 g upon 5. Now the potential energy of the spring loss we know as 0.25 joules. The initial potential energy of the block was 2.4 g upon 5, but this is not the loss of potential energy, mind you. This question is not over here. The important thing which most of the students miss is that as this block went down, there was a block of water over here which is now at this position. People generally forget this thing. Is a very important point which you should keep in mind whenever there is a block or this kind of system inside water and it is falling by a certain height. So in these cases, the important thing which you should always keep in mind is that the block goes down by whatever x distance, and this is an equivalent block of water which was initially at this position, which will be finally at this position. So there is some rise in potential energy of water also which you have to take into account. So the initial potential energy of the system can be, let this reference level was 0, potential energy equal to 0. So let us write the initial potential energy. Initial potential energy was equal to the potential energy of block plus potential energy of the block of water, which is 0 because it is at reference level 0. Therefore the initial potential energy of the system can be written to be 2.4 g upon 5. Now we need to find out the final potential energy of the system. Since the block comes down to level 0, therefore the potential energy of the block is 0, but there is some potential energy of this block of water which was initially here. This block replaced its position, so this mass of water can be assumed to be taking the position of the block. Therefore, the potential energy final of the system comes out to be equal to the mass of this block of water, that is mass of block of water equal to the weight of this of 1.2 kg mass. Therefore, the volume of this block was 1.2 upon 6000. This is the volume of water which is moving into 1000. This is the mass of water that is moving by height equal to 40 centimeters. This is equal to mg into 40 upon 100. This comes out to be equal to 0.2. This is 0.2. This is 2 by 5. This comes out to be equal to 0.4 g upon 5. So the initial potential energy was 2.4 g upon 5. The final potential energy is 0.4 g upon 5. Therefore, the loss in potential energy is P initial minus potential energy final, that is equal to 2 g upon 5. So the loss in potential energy is not 2.4 g upon 5. The loss in potential energy is something less than 2.4 g upon 5, that is 2 g upon 5, because since this block loses some potential energy, there is also some block of water which is gaining some potential energy. Now we can find out the total loss in energy. So we can analyze the full picture now. This spring loses some potential energy. The system of block and water also loses some potential energy. So the total loss in energy is equal to 2 g upon 5 plus 0.25 joules. Therefore, this comes out to be equal to 4.25 joules. Therefore, this is the amount of energy that is lost, and this is the amount of energy which is used to rise the temperature of water and block system. Therefore, we can write this as 4.25 is equal to, let the rise in temperature of each of them be delta T. Therefore, 4.25 is equal to mass of block, that is 1.2, into specific heat of block, that is 250, into delta T, plus the same amount of heat is also utilized to rise the temperature of water by the same amount, that is M 260 upon 1000, into specific heat of water, that is 4200, into delta T. On solving this equation, we get delta T is equal to 0.003 degrees Celsius. So final answer for the rise in temperature of water comes out to be equal to 0.003 degrees Celsius. The important thing which we learned in this question, and which you should always remember, and do not please commit this mistake, that whenever there is loss in potential energy of block inside water, there is an equivalent volume of water which is going upwards to make some rise in potential energy. So the net loss in potential energy is lesser than the value you expect. So the final answer comes out to be equal to 0.003 degrees Celsius.